Hey guys. So today what we're going to look at is really the birth of modern medicine. It's what we call germ theory. Now, germ theory is the idea that stands behind vaccines, that stands behind modern medical diagnoses and treatments. Germ theory is what allows us to have antibiotics, and it's what allows us to be able to conduct surgery without the threat of infection. Now, this theory is a long way from these slavish recitation of classical medical theories, bloodletting and balancing bodily humors, the sort of things that characterized ancient and medieval Western medicine. So how did we get from those ideas that really hadn't changed since the days of Hippocrates and Galen? How did we get from there to a modern understanding of disease and medicine? Well, today we're going to look at the work of three different individuals in the development of germ theory. And we're going to see that though this wasn't a rapid process, it really was a case where individual achievements pushed science forward. Now, the first individual we're going to take a look at today is Anthonie van Leeuwenhoek. Now, van Leeuwenhoek lived from 1632 to 1723. He was a Dutch tradesman and scientist and sort of more or less a small businessman. Now, his work as a scientist was more or less incidental. He was a manufacturer of microscopes. He produced these little items, almost 200 of them in his lifetime, and he became known as the world's best producer of these microscopes. It takes a lot of effort and a lot of art to be able to produce glass that's clear and round and produces a good image. As you can tell, the lens in this microscope doesn't look anything like a common compound microscope that we'd use today. It's really just a little glass bead that's going to bend the light and amplify an image. Now, as this microscope, if you look at something under this microscope, you put the object on the top of the little pin and move it around using the thumb screws until it's in focus and until you're looking at the proper part of the image. Now, his principal business, van Leeuwenhoek, actually became selling these microscopes, but he was always very jealous about the way he guarded them and always kept the best ones for himself. Now, one of the things that van Leeuwenhoek did that really made him revolutionary in this field was he kept very careful recordings of everything that he saw under his microscope. He looked at things like muscle fibers, blood cells, nerve cells, and perhaps most surprisingly of all, he looked at drops of water. Now, within these drops of water, he saw these tiny little swimming items. He didn't know what they were, so he called them animalcules, kind of like an animal molecule, tiny little animal. It's an animalcule. Now, these animalcules, he had no idea that they were causing disease or something like this, but he had actually observed the first single-celled organisms all the way back in 1676. Now, he even used his microscopes to calculate the number of microorganisms per unit of water. So, though he didn't understand that these were agents of disease, he was actually figuring out some sort of measure of water clarity. He also was important in a term that we all use today, the cell. By looking at wood, he saw these strong cell walls and noticed that the little individual objects that he was observing in the wood looked like the cells in which monks lived. And thus, we came to know the basic unit of life as a cell. Now, van Leeuwenhoek gave his findings to the Royal Society in London, which eventually disseminated this information widely. Now, the next person we're going to pick up with is Louis Pasteur. Now, Louis Pasteur was a French chemist who lived between 1822 and 1895. And among other discoveries, Pasteur characterized, for example, enantiomeric molecules. They're molecules that have left and right-handedness. But he's best known today for his work in microbiology. Now, Pasteur was trying to experiment to understand why food spoiled, why food and drink spoils. Now, in doing so, he ended up coming into contradiction with the prevailing theory of the day, which was spontaneous generation. The idea of spontaneous generation is that non-living objects can basically spring to existence from, that living objects can spring to existence from a non-living background. So the idea is that if you have, I don't know, meat sitting out, well, flies come out of the meat. Or if you have bread sitting out, mold comes out of the bread. Now, this idea seems a little bit ridiculous to us today, but at the time, this seemed pretty reasonable considering you can't see anything going and landing on your bread that's going to produce mold. It isn't like mold wanders over and jumps onto your bread and causes that. You can't see the spores that are going to be causing the mold. Now, this spontaneous generation idea was principally championed at the time by another French naturalist named Félix Pouchet. Now, he was actually studying the process of ovulation and correctly determined that an egg is produced spontaneously rather than in response to some sort of fertilization event. So he said if eggs are produced de novo, then this idea of heterogenesis stated that the eggs of an adult organism could be spontaneously created from non-living matter. Now, Pasteur, in his study of spoilage, looks at whether spoilage is a result of contamination from the air. And he discovers that in the solid particles that float around in the air, you can actually find microorganisms. Later on, he took broth, heated it, and put it in a sealed container. He showed that that broth would not go bad. Now, that's some evidence that maybe you need contamination from the air to cause something to spoil, but a lot of people, Pouchet included, said, no, this really doesn't hold water. The idea is, well, you might need air to grow. You wouldn't be able to grow without air, so whatever's spoiling in there probably needs air. You keep it sealed up, well, you're not giving it an essential element of life, and the stuff's not going to grow, regardless of where it is. So, in order to refute this claim, Pasteur comes up with a really beautiful experiment. And he debuts this experiment actually at a large conference. Pasteur develops what he calls a swan neck flask. And you can see that the swan neck flask has a long sort of glass tube that extends away from the body of the flask. Now, Pasteur puts broth into this flask, some kind of, animal broth, and he boils it to kill any microorganisms that might exist there. And the broth stays fresh. He talks and puts this broth up on stage with him. And the broth sits there during this conference, during weeks or days and days of discussions and talks and something like that, and it doesn't go bad. The reason is that little tube that leads to the broth is so convoluted, nothing can really get through. So it basically serves like a filter. Now, Pasteur talks about how there are germs in the air, the germ of life. Now, he's not using it to mean disease, he's using it to mean like the start of something, like wheat germ is a seed for wheat. So he talks about how these germs carried by microscopic dust, those are the agent of spoilage. And he breaks the neck of the flask. Now, once the neck of the flask is broken, all of a sudden, those germs have access to the broth. And only a short time later, the broth in the flask spoils, and he's shown that this broth, when exposed to the air, all of a sudden, it can spoil. Now, the thing was, you couldn't refute this. You couldn't say, oh gosh, he didn't give it air, because the air could get in all of the time through that convoluted little swan neck flask. It was just the dust wasn't getting in. So he was showing pretty clearly that germs, these unseen microorganisms, were actually the agents for spoilage. And it wasn't long before people understood that they were also the agents of disease. Now, Pasteur was responsible for a lot of medical advancements, including many vaccination programs and other things. But the person who really took Pasteur's ideas and revolutionized surgical medicine was a man by the name of Joseph Lister, who lived from 1827 to 1912. Lister was a Quaker who was educated at University College London. And he, at that time, when Lister was a young surgeon, post-operative infections were rampant. In fact, surgery was pretty much a death sentence. It was a 50-50 chance that someone would get an infection and die. Lister became curious about why certain people would survive and certain people wouldn't. There were certain wards in hospitals where more people would become infected postoperatively and other wards where people would be okay. He tried to understand, was it the light, was it the heat, something like this. Eventually, Lister reads Pasteur's work, and he sees that 3 techniques can really reduce bacterial contamination: filtration, heat, and exposure to chemical solutions. Now, if bacteria and some sort of microorganisms are causing food spoilage, they're probably causing infection too, and Lister thinks, gosh, well, we can't really heat up someone in surgery. We can try our best to filter things out of the air, but let's try for this chemical solution to try to treat surgical instruments. So he takes carbolic acid and swabs wounds and surgical instruments and even the hands of the surgeons. And he finds that the incidence of postoperative infection, gangrene, and things like this go way down. In 1867, he publishes Antiseptic Principle of the Practice of Surgery, and he makes the recommendations that surgeons should wear clean gloves and surgical gowns. They should wash their hands and surgical instruments with carbolic acid, and they should use non-porous handles on surgical instruments. Now, these recommendations seem very, very specific. However, it should be noted that people really didn't get it. Many doctors, especially those in America, were sort of unwilling to accept that something so small that it couldn't even be seen could cause illness to a grown human. And even if they were trying to implement Lister's techniques, they often missed. For example, if they dropped some sort of scalpel during surgery, they'd often pick it up off the unsterilized ground. They would hold instruments in their mouth during surgery. And in fact, it was a standard practice for people to wear dirty, filthy surgical clothing. In fact, it was said to have a good surgical stink because you wanted to show that, well, this wasn't your first rodeo. You wanted to show that, yes, I performed surgery before and I have the blood of the last guy to prove it. And so very often, whether or not the surgeon had sterilized other things, his coat would have the remnants of the last patient that might spread an infection. Now, it's important to realize that modern surgery isn't actually conducted in the same way that Lister was recommending. Lister recommended what's known as antiseptic surgical practices. Now, what he was trying to do, he was trying to actively kill disease-causing agents, kill the bacteria, kill the germs that might cause a postoperative infection. Modern surgery operates under what we call an aseptic principle. The idea is that we wash our hands, we keep our clothing clean, we sterilize instruments, and thereby we stop any disease-causing agents from gaining access to the wound by simply making a sterile surgical theater. Now, Lister's recommendations were more quickly adopted in Europe and more slowly in the US. One of the things that caused Lister's recommendations to be accepted in the US was actually the failed assassination attempt on President Garfield and Garfield's subsequent death due to an infection that was brought about probably by actually the medical treatment he received. It took something as catastrophic as the president dying preventably to get people to reconsider medical practice, kind of in the same way that it took something as catastrophic as the bubonic plague to get people to reconsider some of the medical truths that they had been holding on to before. I hope that you guys have found this interesting, and I look forward to talking to you next time when we're going to take a look at how antibiotics have changed our world.